I welcome you all to the week 9 live interactive session for the course Chemical Reaction Engineering 2. Now let's get on to the session. So let's have a brief recap of lectures of week 10. So week 10 had 5 lectures, of which the first 3 lectures were on fluid solid non-catalytic reactions, and the last 2 lectures were on residence time distribution non-ideal reactors. So the lecture 46 included conversion as a function of unreacted core size, plotting conversion as a function of unreacted core size for diffusion control for a shrinking core model. And then the expression for time, time and for 100% conversion time when the reaction is rate controlling, again for a shrinking core model were discussed. This was followed by discussing on reaction rate controlling and film diffusion controlling when particle size changes, that is when particles shrinks. uh, so this was followed by lecture 47. In lecture 47, the expression for T by tau for spherical particle, flat plate and cylindrical particle for shrinking core model was discussed. And then a problem was initiated on dissolution of solid particles. It was on pharmacokinetics, basically dissolution of your drug, where particles are monodispersed, that is all particles have the same size, was discussed in the lecture 47. And the next lecture was on fluid solid non catalytic reaction, where the same dissolution of particles problem was solved when the particles are polydispersed, that is the particle size varied, and there was a distribution in particle size. The lecture 49 was an introduction to residence time distribution, where an introduction was given on distribution of residence time in case of ideal and what happens in case of a real systems, and then analysis and characterization of non-ideal behavior was introduced, and distribution of residence time in case of a gas liquid reactor was discussed, and then what are the source of non-ideality, possible non-ideality and residence time distribution in case of a packed bed reactor was discussed. And lecture 50 was again on residence time distribution, and here CSTR was discussed, and then 3 concepts of identifying non-ideality in reactors were discussed, and how to approach what are the design approaches for a real world reactor, and residence time distribution for ideal PFR, ideal batch reactor, and then CSTR were discussed. And how do we measure residence time distribution? What is a tracer, and what are the characteristics of tracer, and what are the injection methods for finding out the residence time distribution for a trace? Injection methods for a tracer were all discussed. Now let's get on to the week 9 practice assignment. Question number 1. Calculated the time needed to burn to completion for particles of graphite of radius 5 mm and density of 2.2 gram per centimeter cube and specific reaction rate constant of 20 centimeter per second in an 8% oxygen stream. For the high gas velocity used, assume that film diffusion does not offer any resistance to the transfer and reaction. The reaction temperature is at 900 degrees centigrade. So here they have given graphite particles and they have given the density and the radius and specific reaction rate constant when it is reacting in a stream of oxygen, and the concentration of oxygen is also given, and the temperature at which the reaction takes place is also given. They have asked us to find out the time needed to for complete burning of this graphite particles. So how to approach this problem? So given the material is burnt in oxygen, the burnt in oxygen is graphite. So graphite is nothing but a carbonaceous material. So reaction of carbonaceous materials occurs by particle size shrinking. So this implies that since the particle size is shrinking with the reaction, there is no ash layer formation and there is no ash layer resistance as well. So the two possible mechanism for rate control for this type of reaction where the particle size shrinks with the reaction is gas film diffusion and the reaction control. They have also given that the gas film does not offer any resistance to reaction due to high gas velocity. That means the only source of rate controlling mechanism is the reaction rate control. So, what is the expression for complete conversion time for reaction control for a shrinking particle? And also, since they have given the radius as 5 mm, we are considering it to be a spherical graphite particles. So, the expression is for complete conversion is tau is equal to rho b into r divided by b into k double prime into CAG, where rho b is the density of the solid, r is the radius of the initial radius of the solid, b is the stoichiometric coefficient of the solid particle, and k double prime is the specific reaction rate constant, and CAG is the concentration of the fluid stream. Okay. Now, so we already have the density of the solid, which is given as 2.2 gram per centimeter cube, and the radius of the graphite particle is also given as 5 millimeter, which is nothing but 0.5 centimeter. They've also given specific reaction rate constant K double prime is equal to 20 centimeter per second. Now, what is the type of reaction? So, the type of reaction is C plus O2 gives CO2 because it's a graphite, so nothing but carbon. So, carbon plus oxygen gives carbon dioxide and it's a complete conversion reaction. So, the coefficient of carbon here is 1. So, B is equal to 1. Now, next step we have to find out is the concentration of oxygen CAG. So, they have given that the oxygen stream is 8%. Okay, 8% oxygen stream is reacting with the graphite particles. So, we have to assume that the given percent, they have not given whether it is 8 mole percent or 8 weight percent or 8 volume percent, anything. So, let us assume that the percentage given is to be mole percent. Okay. Now, concentration of oxygen at standard temperature and pressure is, so standard temperature and pressure is 273 Kelvin and 1 bar, which is given by N by V, where N is the number of moles and V is the volume. Volume occupied by the gas at standard temperature and pressure. So, the volume occupied by 1 mole of gas at standard temperature and pressure is 22,400 centimeter cube. Okay. So, now we can calculate CAG, that is the concentration of oxygen at standard temperature and pressure. So, N by V. So, N they have given 8 mole percent. So, 8 by 100 divided by V, that is 22,400. That will give you 3.57 into 10 power minus 6 mole per centimeter cube. Now, this is the concentration of oxygen at standard temperature and pressure. So what we have to find? We have to find out the concentration of oxygen at a temperature of 900 degrees centigrade, because they have given the reaction temperature is 900 degrees centigrade. Now given temperature is 900 degrees centigrade, so converting it to Kelvin, which is nothing but 900 plus 273, that is 1173 Kelvin. Now let us assume that even at 900 degrees centigrade, let the pressure be 1 bar. Okay, and then assuming ideal gas law, PV is equal to nRT. So P is equal to N by V into RT. So N by V is nothing but your C concentration. So P is equal to CRT. So rearranging this for condition 1 and 2, we will get. So here again, your pressure is constant 1 bar for both the cases, and similarly your R is your universal gas constant. So the only the set of varying parameters are your concentration and temperature. So they inversely vary. So CAG at 273 by CAG at 1173 is equal to T2 by T1. So we know what is T2, which is 1173, and we know what is T1, which is 273. So CAG at 1173 is CAG at 273 into T1 divided by T2. So CAG at 900 degrees centigrade or 1173 Kelvin is 3.57 into 10 power minus 6 into 273 divided by 1173, which gives the concentration of oxygen at 1173 Kelvin to be equal to 8.31 into 10 power minus 7 mole per centimeter cube. Now we have got the concentration, and then density is already given, radius is already given, V we have found out, and K double prime is also given. Now let us substitute all the parameters. So tau is equal to rho B R divided by B into K double prime into CH. So which is equal to, so substituting it, so 2.2 gram per centimeter cube into 0.5 centimeter divided by 1 into 20 centimeter per second into 8.31 into 10 power minus 7 mole per centimeter cube. So if we look into the step, now we can cancel and find out what is the unit that we are ending up with. So the actual unit should be some time units, because this is the time for complete conversion. So either it can be seconds, or it can be hours, or it can be minutes. So any time unit can be there. But let us see what is the actual unit we are getting. So if we just look into this, so we can cancel centimeter. Similarly, your centimeter cube gets cancelled. Whereas what we end up with this, so the second will go to the numerator. So gram second per mole is the unit what we end up with. Right? Because this density is in gram per centimeter cube, whereas your concentration is in mole per centimeter cube. Right? So now what we have to do to make unit consistency? So we have to convert either density to mole per centimeter cube or concentration to gram per centimeter cube. Right? So now converting the density to mole per centimeter cube. How can we convert the density of the graphite or carbon material to from gram per centimeter cube to mole per centimeter cube? So we can divide it by its molecular weight. Right? So molecular weight for carbon is 12 gram per mole. So what we can do, so rho B is equal to 2.2 gram per centimeter cube divided by 12 gram per mole, and we will end up with 0.183 mole per centimeter cube. So this is what is the density in mole per centimeter cube. So once we incorporate this into the conversion to complete conversion time equation, we will have a unit consistency, and we'll end up with units in seconds. Okay, so substituting all the values, we will end up with 5505.4 seconds, which comes to approximately 1.5 hours. So the time for complete conversion of graphite particles of radius 5 millimeter is, with an 8% oxygen stream, is 1.5 hours. Okay. Now Let's go on to question number 2. On doubling the particle size from R to 2R, the time for complete conversion triples. What is the contribution of hash diffusion to the overall resistance for particle size R? So they have given two conditions. So where in condition 1, your radius is R1 is equal to R, whereas in condition 2, your R2 is equal to 2R. And they have given a relationship between the complete conversion time for R1 and R2. What they have given? So they have given that as the radius doubles, the complete conversion time triples. That means tau 2 is equal to 3 times of tau 1. Now they have asked us what is the contribution of hash diffusion to the overall resistance for the particle size R. So now let us assume a shrinking core model, and since they have asked for hash diffusion, we can also take that the particle size is going to be constant, only the unreacted core is going to shrink. So it is going to have some non-flaking thick ash layer. Okay. So the mechanism controlling the reaction rate are, it can be gas film diffusion, ash diffusion and reaction diffusion. So three mechanisms controls the reaction. Okay. Now time for complete conversion, tau is given by time due to time for complete conversion if gas film diffusion is going to dominate, plus time for complete conversion when ash diffusion is going to control, plus time for complete conversion when reaction is going to control. Okay. Now we can also write for particle 1 and 2. So tau 1 is equal to tau G1 plus tau A1 plus tau R1, and similarly tau 2 is equal to tau G2 plus tau A2 plus tau R2. Okay. Now the next step is, what is the expression for tau G, tau A and tau R when for a shrinking core model with constant particle size? So tau G is given by rho B into R divided by 3B kg into CAG. Similarly, tau A is given by rho B R square by 6B dE into CAG, and tau R is given by rho B R by B into K double prime into CAG. So of these, all the other parameters, we only have information on the complete conversion time between the two particles and also the radius of two particles, where the radius R2 is twice that of R1. Okay. So from the above set of equations, from these expressions for complete conversion when gas film controls, when ash diffusion controls and when reaction controls, we can find their relationship with the particle size. So where complete conversion for gas film controlling is proportional to R. From this expression we can find it out. And similarly ash diffusion is proportional to R square, and reaction control is again proportional to R. Okay. So when R2 is equal to 2R, then tau G2 will be 2 proportional to 2R, tau A2 will be 2 into R the whole square, and tau R2 will be proportional to 2R. That means tau G2 is equal to 2 times of tau G1. Right? Because it is proportional to R, here it is 2R. It is proportional to R square, it is proportional to 4R square. Here it is proportional to 2R and proportional to R. So tau G2 is equal to 2 times of tau G1, tau A2 is equal to 4 times of tau A1, and tau R2 is equal to 2 times of tau R1. Now we have this expression for tau 1 and tau 2, and we also have the relationship between tau G2 and G1. Similarly, tau R2 and tau R1, and tau A2 and tau A1. right? So from the above relation, we can get tau 2 is equal to 2 times of, because tau 2 is equal to tau G2 plus tau A2 plus tau R2. So we have their relationship with tau G1, tau A1 and tau R1. So tau 2 is equal to 2 times of tau G1 plus 4 times of tau A1 plus 2 times of tau R1. Right? And also we have tau 2 is equal to 3 times of tau 1. So substituting that in the above expression, you will get 3 tau 1 is equal to 2 into tau G1 plus 4 into tau A1 plus 2 into tau R1. Right? So solving 1 and 3. So expression 1 gives tau 1 is equal to tau G1 plus tau A1 plus tau R1, which is when particle size is R. And expression 3 gives 3 tau 1 is equal to 2 tau G1 plus 4 tau A1 plus 2 tau R1, which is when particle size is 2R. Okay. Now solving these two, we get tau A1 is equal to tau G1 plus tau R1. Right. So substituting this relation of tau A1 is equal to tau G1 plus tau R1 into the expression 1, we will get 2 tau A1 is equal to tau 1. So tau A1 is equal to 0.5 of tau 1. That means ash layer contributes 50% of the total conversion time for radius R. That means it offers 50% of the total resistance for conversion of, the particle of size R. Okay. Now let's go on to question number 3. Spherical solid particles containing B are roasted isothermally in an oven with gas of constant composition. Solids are converted to a firm non-flaking product non-flaking product according to shrinking core model as follows. So A in gas phase plus B in solid phase gives R in gas phase plus S in solid phase, where Ca is equal to 0.01 mole per liter, rho B is equal to 20 gram per liter. From the following conversion data by chemical analysis or core size data by slicing and measuring, determine the rate controlling mechanism for the transformation of solid. So they have also given a table where they have given diameter of the particle from the core slicing and measuring, and also conversion by chemical analysis and the time. Okay. So diameter they have given 1 and 1.5, and conversion and they have given 1 and 1, and time in seconds as 200 and 450. Now what are the informations we can take from this to identify what is the rate controlling mechanism? First of all, they are given spherical solid particles. So conversion of solid to non-flaking product. So they have given non-flaking product. That means particle with constant size. Only the unreacted core is going to shrink, whereas the particle size is going to remain constant. So for shrinking core model with constant particle size, what are the mechanisms controlling the rate? They can be either gas film diffusion, ash diffusion or reaction diffusion. Either all the three or any one of these or a combination of two are possible mechanisms. Okay. Now from the given data we have to find out which of these is the mechanism. So from the table we find that for both the diameters conversion is 1. XB is given as 1. Right? XB is given as 1. So we can consider whatever time is given as, because this time corresponds to the time for this particular set of conversions. So that means since the conversion is 1, that means the time is nothing but your complete conversion time tau. Right? So these are some of the inferences which we can take from the data. Suppose if your xb is given as zero point 0.5 and zero point 0.3, then the t is only just t. Since it is given as xb is equal to 1 and 1 in both the cases, so we can take whatever time is, because this time is nothing but the time for this time to achieve this particular conversion. So this particular conversion is nothing but your 100% conversion or complete conversion. That means we can the time given is nothing but your time for complete conversion, that is tau. So now, so the relationship between the diameter or radius and the time for complete conversion for different mechanism controlling the rate is given by, this is for shrinking core model for constant particle size. So from even in the previous question we have written this similar expression. That means, so tau g, so time for complete conversion if the gas film is controlling is given by rho b into r by 3b kg into cag, right? And tau, where your rho b is the density of the solid, r is the radius, and b is the stoichiometric coefficient of the solid, kg is your mass transfer coefficient through the gas fill, and cag is your concentration of the gas. And tau a, that is time for complete conversion if the ash layer is controlling, ash layer diffusion is controlling, it is given by rho b is tau a is equal to rho b into r square by 6b into de into cag, where rho b again is your density of the solid, and r is the radius of the solid particle, b is the stoichiometric coefficient, de is the diffusion constant or your diffusivity through the ash layer, and cag is again your concentration of the gas phase. Okay, concentration of the gas phase component. And similarly, tau r, which is nothing but your time taken for complete conversion when the reaction is the rate controlling step, then which is given by rho b into r divided by b into k double prime into cag. There again rho b is the density of the solid, r is the radius of the particle, p is your stoichiometric coefficient, k double prime is a specific reaction rate constant, and cag is the concentration of component in the gas, concentration of the gas phase component. Okay, now here from this we can find out tau g is proportional to r, tau a is proportional to r square, and tau r is proportional to r. So if tau 1 by tau 2 is equal to r1 by r2, then it can be gas diffusion or reaction controlling, because in both the cases they are proportional to r. Whereas if tau 1 by tau 2 is equal to r1 square by r2 square, then it can be ash diffusion control. So what we have to do, we have the tau 1 and tau 2 values, r1 and r2 values. We have to find which of the LHS and RHS matches. Whether tau 1 by tau 2 matches with r1 by r2, or tau 1 by tau 2 matches with r1 square by r2 square. So we have to find out which of these are going to match. So we have r1 by r2 is equal to, so r1 is, so d1 they have given it as 1 millimeter, and d2 they have given it as 1.5 millimeter. That means r1 is 0.5 millimeter and r2 is 0.75 millimeter. So dividing that you will get 0.667, whereas r1 square by r2 square is 0.5 square divided by 0.75 square. So we will get 0.444. Now we can find out what is tau 1 by tau 2. So tau 1 they have given it as 200, tau 2 they have given as 450. So 200 by 450, we find it to be 0.444. So now we can look into the data. So this tau 1 by tau 2 value is same as r1 square by r2 square. That means ash layer diffusion is controlling the reaction. Okay. Now let's go on to next problem. A batch of solids of uniform size is treated by gas in an uniform environment. Solid is converted to give a non-flaking product according to the shrinking core model. Conversion is about 7 by 8 for a reaction time of 1 hour. Conversion is complete in 2 hours. So what mechanism is controlling the reaction rate? So what is the solution for this? Here again they have given conversion of solid to non-flaking product. That means the particle size is going to be constant throughout the reaction. So shrinking core model with constant particle size is to be assumed. Next, they have given when t is equal to 1 hour, xb is equal to 7 by 8. So when time is 1 hour, your conversion is 7 by 8. And they have also given time for complete conversion, tau is equal to 2 hours. Right? Now, when t by tau is equal to xb, it is gas diffusion controlling. This is for shrinking core model with constant particle size. Similarly, when t by tau is equal to 1 minus of 1 minus xb the whole power 2 by 3 minus 2 into 1 minus xb, then it is going to be ash diffusion controlling. And the third case, when t by tau is equal to 1 minus of 1 minus xb the whole power 1 by 3, then it is going to be reaction controlling. So what we have to do is, they have given t, tau and xb. So what we have to do is that we have to substitute their values in the above 3 equation. That is the gas film gas film controlling T by tau expression, ash diffusion controlling T by tau expression, and your reaction controlling T by tau expression. And we have to find if which of these left hand sides of the expressions are matching with the right hand sides of the expression. So whichever expression where the left hand side matches with the right hand side, that corresponding reaction mechanism is going to be the reaction controlling mechanism. Okay. Now T by tau is equal to xb. And let's take the case 1 of gas diffusion controlling. T by tau is equal to xb. So T is 1 and tau is 2. So 1 by tau is not equal to 7 by 8. This means that the gas diffusion is not controlling the rate. Okay. So that is ruled out. Now the next expression is for ash diffusion controlling. So T by tau is equal to 1 minus of 1 minus xp power 2 by 3 minus 2 into 1 minus xp. Here we know T by tau is 1 by 2, that is nothing but 0.5. So 1 minus of 1 minus xb power 2 by 3 minus 2 into 1 minus xb. What is it? So we have to substitute the value of xb, which is 7 by 8. So that is equal to 1 minus of 1 minus 7 by 8 whole power 2 by 3 minus 2 into 1 minus 7 by 8. So that will give you the expression value to be 0.5. This means the left hand side of the ash diffusion controlling expression of T by tau is matching with the right hand side, because both are giving 0.5 and 0.5. So that means the ash layer is controlling the reaction rate. Now we shouldn't stop, but with the given information we should also try and see what happens when the reaction is controlling. So T by tau is equal to 1 minus of 1 minus xb the whole power 1 by 3. So again T by tau is nothing but 0.5. So 1 minus of the right hand side is 1 minus of 1 minus xb power 1 by 3. So substituting the value of xb here, so 1 minus of 1 minus 7 by 8 the whole power 1 by 3. Here again you will end up with the right hand side as 0.5, which means the right hand side is matching with the left hand side. That means the reaction controlling. So that means the reaction is controlling the rate. So both are giving same. So it can be observed that the equations are satisfied for both ash layer and reaction control. So it can be either of them controlling or one of them controlling. Right, individually contributing or one of them controlling. So for which we need much more information. So we have to closely look into this reaction so that we can find which is the actual reaction controlling mechanism. So whenever we get these kind of problems, we shouldn't stop once we get the left hand side equal to right hand side for any of the mechanism controlling. We have to try for all the mechanisms so that we may end up with this kind of cases where two mechanisms satisfy the the expression for two mechanisms, two or more mechanisms satisfying the expression. Okay. Now let's go on to question number 5. The dash and dash are the only two types of reactors in which all the atoms in the reactors have exactly the same residence time. Which are the two types of reactors for which all the atoms in the reactors have exactly the same residence time? So the answer is, it is for ideal plug flow reactor and ideal batch reactor. Okay. Now the next question. What are the most common source of non-ideality in CSTR? So in CSTR, the bypassing and the dead zones are the most common source of non-ideality. So that is why we didn't have an ideal CSTR which has the same residence time for all atoms in the reactors, because in CSTR what happens is that there are chances of bypassing. That means the particles entering may leave the reactor immediately. So in most of the cases, as discussed in the lectures, it is discussed in the lectures also. So in most of the cases of CSTR, the inlet and outlet can be very close to each other, and the reactants may pass through the reactor immediately, may pass out of the reactor immediately without really getting mixed or participating in the reaction. So that part of the reactants, I know, they have very low residence time. Whereas there are dead zones also in the CSTR where which doesn't get mixed. It may be in the corner in the bottom of the vessel. So which does not, participate in the reaction, and they stay in the reactor for a long time. So in the case of CSTR, these two actually causes non-ideality, which makes it that all the atoms does not have the same residence time. So there may be particles which can pass out of the reactor very soon, and there may be a portion of reactants which stay in the reactor for a very long time. So these causes non-ideality in the case of CSTR. The next question is, for a freely freely falling particles in the Stokes law regime, with the particle size changing during the reaction, the gas phase mass transfer coefficient is it similar to diameter of the particle, or is it similar to 1 by square of diameter of the particle, or is it similar to square of diameter of the particle, or is it similar to 1 by dp? So for the Stokes regime, for small particle sizes, uh, for small particle sizes, the kg is proportional to 1 by dp. So I missed, there is an error in the question. I missed the term small particle sizes. When it is large particle sizes, it becomes, the equation changes. Okay. It becomes, kg is, very closer to square root of u by dp. That is u power half divided by dp power half. Okay, that is for large dp and large uh, superficial velocity. Whereas this case of Stokes law regime is for small particles and small superficial velocity. Okay. Now let's go on to the next question. Roasting of zinc sulfide is an example of gas solid non-catalytic reaction with. So what type of gas solid non-catalytic reaction is zinc sulfide roasting? Is it a reaction where the particle size is constant, whereas it is having a shrinking unreacted core, or is it having a shrinking particle? So which of that it belongs to? So the roasting of zinc sulfide, it belongs to the category of particle size remaining unchanged with time. So the reaction scheme is 2ZNS plus 3O2 gives 2ZNO plus 2SO2. So the particle will also be, the product particle will also be of the same diameter. Okay. Now let's go on to question number 9. Identify the geometry of the particle for the conversion formula given below for shrinking core model. A is xb is equal to 1 minus r by r naught the whole square. B is xb is equal to 1 minus 1 by L, and C is xb is equal to 1 minus r by r naught the whole cube. So, for which of the geometry the conversion has these kind of expressions. So the answer is, when xb is equal to 1 minus r by r naught the whole square, then it is for a cylindrical particle. Okay. So you have this pi r square h and pi r square h. The shrinking core, unreacted core, and the initial particle diameter as r naught. So with that you will end up with this expression of conversion xb is equal to 1 minus r by r naught the whole square. Whereas for a flat plate, you will have the conversion xb is equal to conversion of the solid particle, where xb denotes the solid particle. So xb is the conversion of the solid particle. So xb is equal to 1 minus 1 by L, where L is the half thickness of the plate. And the third expression, xb is equal to 1 minus r by r naught the whole cube, is for spherical particle, because the volume is going to, the unreacted volume is going to change as the reaction proceeds. So it will be, so 1 minus xb will be equal to volume of the unreacted core. So 4 by 3 pi r cube divided by 4 by 3 pi r naught cube. So that you will end up with. So 1 minus xb is equal to r by r naught the whole cube. So xb is equal to 1 minus r by r naught the whole cube. Okay. The last question for the session is, for a flat plate, T by tau for ash layer control in shrinking core model is equal to, is it equal to xb, or is it equal to xb square, or is it equal to 1 minus 1 minus xb the whole power 1 by 3, or is it xb plus 1 minus xb into ln of 1 minus xb. So which of these expression matches for T by tau for having a in the case of a flat plate, having ash layer as the reaction rate controlling mechanism in a shrinking core model. The answer is T by tau is equal to xb square for ash layer control for a flat plate. Whereas T by tau is equal to xb when it is, that is also for a flat plate, when it is either gas film diffusion control or reaction rate control, or it is also it is also the case for spherical particle with gas film diffusion as controlling. And the third expression, 1 minus of 1 minus xb power 1 by 3 is equal to T by 2 of tau when reaction is controlling the rate for a spherical particle. And the third expression, T by tau is equal to xb plus 1 minus xb into ln of 1 minus xb, is an expression for ash layer ash layer controlling the reaction, the ash layer controlling the rate for a cylindrical particle. Okay, so that's it with the session. So let me also correct the with the particle size unchanging, freely falling particles. diameter and velocity. Okay. So that's it with the session. Thank you all.